introduced yet?
Not yet.
Okay, great. Thank you. All right, Michal will tell us about differential Galois theory.
Yeah, okay. Thanks for having me here. And yeah, so let me start with some context. Okay, so differential Galois theory. I guess Galois, let's say, started, but not differential Galois, but just Galois theory, which is study of symmetries and solutions of algebraic equations, polynomial equations in one variable. And yeah, but okay, but we not the polynomial equations. We also study differential equations, and the groups that use the symmetries of these equations were first considered by Lie. So this is study of continuous groups that we now call Lie groups, and they can be symmetries of some differential equations. So, for example, if we look at the equation x prime equals x, then solutions are c times e to a variable, where the derivative of the variable is 1. And so the automorphism group of the field containing these solutions with a natural derivative over rational functions with the natural derivative on this field. This is just complex numbers. So every complex number represents a symmetry of solutions of these equations, where e to t, we can send it to some multiple of the exponential function. Okay, so this, I guess, during this talk, I will write it as GMC, because this is some algebraic group, and later we'll see that these groups of symmetries of differential equations will always, or under some assumptions, be algebraic groups. So later, these questions, more examples than just this one, was studied by Picard-Vessiot. So this is, as far as I checked, 1990s. And this is homogeneous linear equations. And then later, we have some more development of differential algebra. So we have Kolchin in 1950s, roughly, where he proved fundamental theorem of differential Galois theory. Galois theory has the fundamental theorem providing an isomorphism between lattices of intermediate subfields and subgroups.
Yeah, sorry, really basic question. What do you mean by isomorphisms of C, T, e to the T, comma, del?
Yeah, so I will say it more precisely, but here, this is a field.
Yeah.
And it has an operator, a difference, and this operator, it's an additive homomorphism that satisfies Leibniz's rule with respect to addition. And then you can look at bijections or field automorphisms of this field. So as a field, it just has two independent variables, but that preserve the action of this operator. So,
okay.
Yeah, so del of f of x is f of del of x. Yeah, so, okay. Yeah, so functions from the field to the field such that field automorphism such that f of del x is del of fx. We preserve this differential. And then this is exactly the automorphism. Okay, and there exists, So I will talk more precisely about this fundamental theorem, and maybe we'll even prove it, or sketch a proof. But then later, this is also something that I will focus about a bit. This is 1959. Robinson introduces the notion of differentially closed fields. So of course, historically, differential Galois Galois theory was developed before algebraically closed fields. And I guess this is the same with differential Galois theory, but now when we learn it, we start with, maybe we will learn it simultaneously, but yeah, algebraically closed fields are fundamental for Galois theory. And in the perspective I will present today, I want to also underline the role of differentially closed fields. And also later, there was a lot of treatment of differentially closed fields and by model theorists, model theoretic. So this is Bloom, Wood, Scheller, yeah, and others. Okay, so this is the introduction, but maybe let's get to some precise definitions. So I'll review first Picard-Vessiot theory. So the context is the following. K is characteristic zero field, and it has D derivation. So it's a function from K to K, such that derivation for x plus y is dx plus dy, and derivation of x times y is x times dy plus y times dx. It satisfies Leibniz rule, and these are algebraic structures that one can study. So, of course, I guess the prototypical example will be C of t and the derivative over t. Okay, and then K over L is a differential field extension if they are both differential fields, and if the derivative of L restricted to K is the derivative of K. So yeah, so similarly, okay, if I have two fields, these are like abelian groups that embed into each other, but also the multiplication is preserved. Here we add one more thing, and okay, so fix some differential field KD, and consider the following type of equations. So I will write it as L of y. This will be a differential equation on a variable y, which I will write in this way. So this is n minus 1, right, n minus 1, plus n1 plus a0y equals 0. So L of y is my notation for y satisfies this kind of equation. So really here I mean n time applying the derivative in my differential field or in some extension. And these coefficients are in my base field K. And yeah, okay, maybe we want to solve some differential equations over some particular. So, okay. So now I can define what is a Picard-Vessiot extension. So differential extension K to L is PV, Picard-Vessiot, for the equation L if the following holds. So first of all, L is generated as a differential field. So I will write it in this form. So this means that I can do polynomial operations, division, but also can apply derivatives. So where y1 up to yn are a fundamental set of solutions of L of y in this bigger field. So fundamental set of solutions means that note that solutions of these equations in any differential field, they form a vector space over the constants. So they are linearly independent over constants fields, and this is the set of x in L such that x prime equals 0. For example, constants in this field are complex numbers, but if I start with any field, I look at q of t or r of t or any field, then if the derivative is del over the t, the constants will be just the base field. So yeah, so this is first condition, and the second condition is actually
The
that
fundamental set of solutions will just mean that there are n solutions linearly independent over the constant field. That's what it means, no more.
exactly. And furthermore, I want the constants of L, so let me denote this CL, not to grow. So they contain constants of K because the derivative extends, but I want this to be preserved. Okay. So this is a Picard-Vessiot extension. Okay.
Is it ever the case that you have conditional one without having condition two?
So if constants are not algebraically close, well, I mean, yeah, condition one without condition two.
Why not? Make them rational functions. You could start with some field and you could look at rational functions in some other variable you don't care about.
But it's going to be generated by the solutions, right?
What if it's just y prime equals 0 and you add more constants?
Yeah, okay, yeah, I guess your equation can be y prime equals 0. Yeah, you don't. Okay.
But we can have more than n solutions, or is it known there's more than n solutions?
No, so actually, there will be n solutions that span the space of solutions. But so yeah, you cannot have more than n if they are supposed to be a fundamental set of solutions. Yeah. So okay, so here really the point is that they are it's generated by a full system of solutions. It's like a normal extension in Galois theory.
And does that symbol mean that those are transcendent spaces of L over K?
So this by these brackets, I mean that here I include like I can do I can put the derivative symbol and I can multiply and I can divide. So these are like differential polynomials in the sense that this is the set of
field generated by the yi's. Basically.
But is there anything that rules out that being much smaller than I might think it is?
So they will I mean, this would be quite big, I guess, usually, but okay, no, actually,
It could also
have this differential equation that they satisfy, it would have finite transcendence. Because you have this equation, like, if you go to derivative high enough, you just can present it as a combination of lower derivatives.
What I mean is, when you write that, are you making an assertion that something is generated by something else, or are you making an assertion that, you know, it's generated and there are no relations other
No,
than
just
lines?
generate. Yeah, okay, sorry. Okay. And so now, yeah, okay. So maybe fact is that for every d L like this, Picard-Vessiot extension exists and are unique up to differential K isomorphism. Yeah, so if I have any field which has these properties, in fact, it's determined up to isomorphism. It's like the normal extension of a field generated by all solutions of some polynomial equation. And we define the Galois group of such system of equations by, or the Galois group of L over K to be the automorphism group of L with its derivative over K with its derivative. Okay. And in this case, because the field is differentially generated by these solutions, something that determines an automorphism.
I'm worried about what's the case of the, if L is just the equation y prime equals 0. We were worried about that.
Okay. So,
If there is, if y prime equals 0, then you'd have to be adding constants, right?
yeah, so then L is just a constant. So it's just L equals K then. Yeah. Yeah. So the fundamental set of solutions is just the constant which
We
generates.
wanted n solutions somehow.
Yeah, but okay, like okay. So I guess it's like a degenerate case where these guys can actually belong to K. But yeah. Yeah, it's not. I mean, yeah, the definition is okay, but yeah, that's a different case. And here, note that this Galois group L embeds into GLN of the constants, either constants of L and C, where if I have an automorphism of such a differential field, I can map it to a matrix such that sigma acts on yi. This is K times y1 times yn. So it maps it to a matrix A such that sigma acts by this matrix A on solutions. So this is related maybe to your question that really, if I have this fundamental set of solutions, a set of n solutions of this order n differential equation that are linearly independent over constants, then every solution here will be uniquely written as a combination over constants of this fundamental set. And
Is it true that if you take the yi's and the derivatives of the yi's up through n-1, that those things generate this as a field?
yeah, because you have this equation. So if you take n derivative, you can always present it like this. Yes.
Except for a degenerate case where if you have a linear equation, you only have the nth derivative up to n equals 0.
Okay, and let me say that moreover, this embedding and this and embedding onto a Zariski closed subgroup. So on an algebraic group. Okay. And now we can write the fundamental theorem of this theory, of this version of Galois theory. So we should have two things. One thing is that if I have now H, a subgroup of this absolute Galois group, then I can look at, of course, things that it preserves. And this is a differential subfield now because it acts by differential automorphisms. So this is the set of Y in L such that for all H in H times Y, or H of Y is Y. Then I have the other way around. If I have some intermediate field, then I can look at the set of automorphisms that fix F. So this will be a subgroup of the automorphism that fix just K. And I want to say that this is that these functions define inclusion reversing correspondence between Zariski closed subgroups of this Galois group of L, which we treat as an algebraic group. So later I'll give some more arguments why it's actually algebraic, why it's just not any subgroup. But yeah, we look at them algebraic subgroups of this group and intermediate differential subfields where we have K, F, L. So this is in the Picard-Vessiot context.
If the algebraic group doesn't have like rational points over the constant field, do you need to like actually go over all extensions and then, or like should you really descend what's happening? Separable closure.
So I think as I stated it, I mean, yeah, if the constants are algebraically closed, then it's fine. But if they are not algebraically closed, you look at I think you just look at Zariski closed subgroups defined over the constants.
Yes, but I'm saying even to define the differential Galois group, do you literally take this like the image of the, like I would think that this is the C points of the.
Oh, okay, so here, okay, yeah, okay. If C is not algebraically closed, then I guess I mean that like the corresponding algebraic. Yeah, okay, so.
That makes sense, right? You just extend, you can always extend constants.
Yeah, so you probably just extend to the algebraic closure and then take the subgroup you get there.
Sounds right.
Yeah. Yeah, okay. But okay.
So then the definition of a Galois group doesn't see any rational data though? Like it doesn't see anything about the field that you started with if your base changing.
No, but it incurs the structure of your base field, yeah. So it'll be naturally an algebraic group over your constant field, subgroup of GOS.
Yeah, and also let me also give another point. This is first point here, and the second point is that an intermediate extension F is a Picard-Vessiot extension with respect to some equations, if and only if the Galois group of L over F is normal in the Galois group of L over K. So we have this, and then the quotient of the Galois groups, the Galois group of L over K, divided by the Galois group L over F, is the Galois group of F over K. So this really works sort of like usual Galois theory. And maybe let's consider some examples. So first, take an element of our field. You can think it's a rational, you can think these are functions of the complex numbers. and then take the equation y prime equals a. So this is not exactly an equation of that form, but we can differentiate again. We can look at the equation y bis minus a prime divided by I, y prime equals 0, and assume it has no solutions in K. So then the solution is a formal integral. We have K embedded in K of alpha, where alpha is the integral of A. And by this, I mean, I can take the free differential algebra and divide it by the relation d alpha equals A, and take the fraction field. And so here, if I look at this linear homogeneous equation, the fundamental system of solutions is 1 and alpha. So one of them indeed belongs to the field itself. And look at this embedding explicitly. So here, the Galois group K of alpha over K. I guess the equation that was written here before was when alpha was t, and then this when a was t and alpha was exponential of t. So here we embedded in GL2 of C, and then if I have sigma, it gets mapped to 1, 0, C1, where sigma of alpha is alpha plus constant, because integrals are well defined up to constant. So, this is. So here the absolute Galois group is naturally the additive group, but inside the GL2. So this is maybe example 1. Example 2, we look at L of y. This is the equation y prime minus ay equals 0. So this is, so here we have k, we extended adding. So here again, here. No, it's order 1. Okay, so it's right. So here we have one generator, and this generator is satisfy the relation alpha prime divided by alpha equals a. So this means if we had logarithm, this means this. So this means alpha is exponents of integral of a. And if we have such a solution, here the Galois group is just the complex, the multiplicative group, Gm of the constants. Yeah, so this is exactly the case as in the example at the beginning. And third example is one can actually show that finite extensions. So let's say if the constants are algebraically closed, constants are algebraically closed. This implies that finite extensions are Picard-Vessiot. So finite in the sense of finite field extensions, like they have finite degree.
Finite normal.
Yeah, finite normal extensions. Okay. Yeah, so these will be 3 times. These will be okay. So these are of particular types. I mean, here the Galois groups are finite. Here the Galois groups is GM, GA. So sort of it's either finite or abelian. But there is also a non-abelian context. So maybe let me give you one non-abelian example. So let's consider the sample L of y. This actually appeared 2 weeks ago. P squared y b's. Many things appear, but it appeared on the conference regarding special points. So if you look at this equation, where n is a real number that doesn't belong to 1/2 plus integers, and you look at this over this differential field, then this is Bessel's equation, and here. And here the Galois group is actually SL2C. I think this is Kolchin.
So is there a reason for not allowing constants to get bigger under these extensions?
What is ultimately the reason for constants not to grow? I mean, I guess when the constants grow, it's sort of like it's not a differential phenomena because constants, okay, is there? Yeah, I think of the constants as like the base field. So changing this base field. Yeah, okay. Then you can do some Galois theory over the constants, and this usual Galois theory,
Would there be a problem with mixing it with this, or would they just go together?
No, I think it would rather go together. But okay, the context I feel comfortable in is when you assume that constants are algebraically close. Because okay, maybe this is more classical situation. Although I mean, yeah, you can. Yeah, it doesn't mean that you can talk about that when the constants are like rational numbers, but then okay, like if you want to use this machinery, yeah. Okay.
Somebody gave me this equation. How would they know that it's SL2C? How do I start even to try to figure out what this Galois group is?
Oh, so it's difficult in general. Yeah, so you know, it's like with Galois theory. Someone gives you a polynomial equation in one variable and asks you, okay, what's the Galois group? Or maybe someone asks you, okay, does this finite group appear as a Galois group of something? It's a bit difficult. But so here actually you can also ask this: what differential, what algebraic groups appear, but okay, in general, calculating this group is difficult. Later, maybe I'll say something how you can do it. So, for example, sometimes you can see it as a closure, the risky closure of some monodromy group, and this is how in practice it can be okay. It can be computed, but yeah,
Not here.
Huh?
But not here.
Not here, yeah. Okay, and so I gave these examples because I wanted to give this definition that a differential extension A to L is Liouville. So some people say generalized Liouville if it can be inductively formed using 1, 2, 3. Yes, there are extensions, I guess, that are like the dream of elementary analysis course, that these are equations that can be solved only by taking exponentials, taking e to exponential, taking integrals, e to integrals, and then maybe some finite algebraic equations. And you can do it in any order.
Can you give an example of 3?
3, well, finite extensions, like maybe you are here and you add e to 1/2 t. You take square root of e to t. Okay. So now, okay, so of course, Galois theory was developed to show non-solvability of some equations. And here, this is also the case. And this is this non-abelian maybe setup. So if I have K inside L and inside some M, such that this is Picard-Vessiot and that this is Liouville, then if I look at the Galois group of L over K, and up to finite groups. So I take the connected component, then this group is solvable. In particular, what it proves is that Bessel's equation cannot be solved by these substitutions. So I guess this is very classical mathematics where people were having some equations and they were trying to solve it literally by simple operations, but like they were trying to solve polynomials by ruler and circle, but then sometimes it's impossible. And okay, and this is what we can use to prove this impossibility.
So can you get from this, this is sort of a criterion for having a fundamental set of solutions, right? Can you get a criterion for just having one solution that's expressible using those operations?
I mean, okay. Actually, this is related to what I'll be talking about here, because essentially the point is that if you have nice equation of a different kind than another, then maybe this means that your differential equation is in fact somehow decomposable into some others. So the point is to do some geometry with differential equations. And I want to say something about the setup of differentially closed fields. But yeah, I'm not sure if it answers your question, but okay. So we want to find a right setup to do this differential Galois theory. So it would be nice to have some universal differential fields. So first, let me give you a small definition. So if we have a polynomial over K, where K is a differential field, and I have it in variable x and its derivatives, then order of f, this is maximum of n such that x to n appears. And then I write SF for the partial derivative with respect to this last formal variable. So this is what sits near this variable. Sort of. Okay. And then I can say what are differentially closed fields. So K is differentially closed if for any differential polynomials f and g, with this I mean two elements of this ring. For any of those, such that SF is not zero, G is not zero, and order of F is bigger than order of G. And there is X in K, an actual element, such that f of x is 0 and g of x is not 0. So a differentially closed field, like an algebraically closed field, is a field that solves all.
By the derivative of f with respect to the. Okay, it's not.
It's just a partial derivative with respect to that. Like I treat it as a variable now, like that has maybe a name y.
Do you mean I write f as a polynomial in the x primes and take like the leading coefficient?
I mean, like, you know, I call these variables now maybe y, z, and so on. So I have something like I have maybe x times y times c plus c squared. And then I just say d over dz, where z.
It has nothing to do with the differentiation in the field.
Yes.
Could SF be 0?
So
Easy.
because you have no, but
Oh, don't you just want to polynomial the derivatives of your Here we go.
Yeah, maybe I should take it actually.
Is there some term that it could vanish on the particular x, right?
Yeah, but I mean, it definitely should be able to be zero, but
Characteristic P can be zero.
I don't know, why can't it be zero? Xn is not in the expression.
So you have a polynomial and a bunch of variables, and you look at the biggest named variable that appears in the polynomial. So it means it actually appears, and then you differentiate.
So he said it appears.
yeah, because it's the order, right? So it's the maximum that appears. Okay, so
Are you still working only with that, or are you also allowing more general characteristics? Because when
so for this definition, or maybe this is also for characteristic P, but I thought there was some condition. Okay, let me give an equivalent definition, and we'll figure out what it should be equivalent to, because yeah, I don't know what to solve it. So okay, equivalently, and this is maybe with more geometry, for every variety V inside An over K. So here I'm just talking about polynomial equations. And
is that n the same as that n?
and any n, no, it's the, so here it's for any variety and for any n, and any, oh,
Just let him write this one. This one thing, just so you can see.
and any subvariety of the twisted tangent bundle of V, which I'll soon define, that this is dominant. So this will be some algebraic variety related to V over K. The set of pairs A, dA for A in V, this will be a subset of this guy, intersects W Zariski densely. And here, if V is given by equations in these n variables, let's say f, let's say G1 up to Gm, then I look at then this tangent bundle. This will be given in more variables, x1, xn, and then I have the second copy of the variables that I will call del x1, del xn. Maybe you can think y1 up to yn. And the equations I will take is I will take g1 up to gn, and then I will take partial derivatives of g1 up to gn. So where if g is the sum of ai x to I, then partial d is, and here I do use the derivative of k. So here I have the sum of the derivative on k of ai times x to I plus the sum of ai, and I have d of xi. And this I write inductively until I get to these guys. So for example, del of x1 squared, this will be 2x1 times del squared. Times del. Does it make sense? Yeah, so really the point is that this is a tangent bundle if V is defined by equations over constants. But if V is defined by equations not over constants, this is twisted a bit. Yeah, because okay. Yeah, so if this vanishes, this is literally the tangent bundle.
The relationship between this and the previous definition is supposed to be some kind of Nash-Dellensatz.
Exactly. Yes. Yeah.
Could you just say that like any PV extension, that your constant is algebraically closed, and any PV extension is just your field again? Did you have no non-trivial PV extension?
I think PV would not be enough.
That'd be enough for this. Okay.
Oh, I'm not sure. Yeah, so so
It's for linear equations, but it's kind of like
Okay, this was crazy equations.
yeah. So this is this configuration somehow encodes every possible differential finite type field extension. So okay.
maybe you want this G1 to Gm reduced. So you don't expect, but that maybe you're thinking about reduced varieties, right? Because
Yes, okay. Yeah, so really maybe everything. Okay. So maybe you don't want to talk about this in the range of schemes.
there is something maybe, but
But to say that something is a risky dance, you just talk about the field. And here, fortunately, like in the algebraic setup, we have a theorem, Scheller. So I think this is quite early Scheller. It's like 15 out of this. I'm referring to Scheller's archive, and what he proved is that every differential field has a differential closure that is unique up to ISO, but in general not minimal. So it's sort of like if you look at vector spaces over Q, you can look at finite dimensional vector spaces. Then every finite dimensional vector space is contained in a unique up to isomorphism, countably infinite dimensional vector space over Q, but it has copies of itself inside it. So it's like unique up to isomorphism, but it's not minimal. So here, if you start with a differential field, you can pass to a differential closure of this field, and it will be unique up to isomorphism. It will be unique up to isomorphism of the property that for every differentially closed field L that K embeds to, you will be able to embed like this, but in general it won't be minimal. It can have copies inside it, like K, D, C prime, that are contained, they are intermediate differentially closed fields, but this is not equality, but they are isomorphic. Okay, so is that phenomenon?
So is this because the Galois theory that you were talking about earlier is only for a special class of extensions?
Yes, but you can extend this class, and this is related to some geometry that one can do in this world of differentially closed fields. So let me tell you a few results about that. So now, because of this, one can do some. Yeah, because of this, the world of differentially closed fields is quite flexible. So fix universal. There exists a universal differentially closed field. I mean, okay, it's not. It's like it's universal, maybe in the sense that for every kappa, for every differential field of cardinality smaller than kappa, you can find it there. You can work in a very big differential field, and then, call it, I don't know, C, like complex numbers, and then a subset. This is Kolchin closed. Is Kolchin closed if it is a zero set of differential equations. yeah, I don't have to really work in this universal one. I can work in any differentiably closed field, but then I can talk about Kolchin closed subsets. I can also talk about Kolchin constructible, so it's like an algebraic geometry. And then if I have a variety V, it has, so variety, I mean now Kolchin variety, so it's a Kolchin closed subset, and it has a Kolchin topology, where Kolchin closed sets are intersections of Kolchin closed with V. So one can relativize the Zariski picture to this differential setup, and it is Noetherian. It is Noetherian. Also, let me say quantifier elimination / Chevalier's theorem. Holds. So by this I mean if I have a Kolchin constructible set, so this is a Boolean combination of Kolchin varieties, and I project it onto some number of variables, I still get something Kolchin constructible. So it's like Chevalier's constructibility theorem that holds here. And then there's also Nurstelen that's in this setup, which sort of already showed up here, that Kolchin closed subsets are in bijection with radical then invariant ideals of such rings. But now maybe I have n variables. So also there's no Stellensatz.
Is it possible to give explicit examples of differentially closed fields, like power series constructions?
So it's okay. So yeah, if you look at power series and you like iterate some, I think there are some constructions, but they're not very nice. Like if you take, for example, germs of holomorphic functions and the algebraic closure, then yeah, I don't think this is differentially closed. So
I think the difficulty is if you take power series, a differential equation does not have to have power series solutions. If it's linear, you can power series times exponents, but like there's no ansatz. There's where you can always find the solution of a general nonlinear differential equation. So it's take some like direct limit holomorphic functions along stuff like moving disks, or it has to be something more.
Yeah. So these differential closures are a bit abstract, but yeah, but algebraic closures maybe are also a bit abstract because we don't even know their automorphism groups. But okay. But anyway, so yeah, so somehow the problem is that one could pose in this geometry is classified Kolchin closed sets, or Kolchin varieties. Yeah, so we try to do this in the algebraic geometry setup. We try to classify sets that are zeros of polynomial equations over algebraically closed fields. So one could try to classify something here. And in algebraic geometry, the building blocks are curves, things that are we cannot vibrate by lower dimensional objects. So here, this classification, it sort of exists because this world is more rich and one cannot do as much as in algebraic geometry, but it starts with the following definition: a Kolchin closed set is strongly minimal if every proper Kolchin closed subset is finite. So we have Noetherian topology, we can talk about dimension, and we can try to classify one-dimensional things. Okay.
How to mention n here? Is the Paul dimension of c to the n, or is it bigger?
It's so no, it's bigger. It's omega. So like you have you have a rank here. Well, you have various ranks. You have various notions of dimensions. But yeah, maybe like an example of something strongly minimal is not the whole field, but just the constants. So the constants are strongly minimal. But then the problem is that the whole field is filtered by these. You can look at increasing unions of sets where first derivative is 0, second derivative is 0, and so on and so on. So they should have bigger dimension, like infinite dimension. Okay. And you know, I have to do maybe some strategy because I won't be able to give the proof. Yeah, so maybe I'll just mention some things. So, okay, so for example, regarding this generalization of Picard-Vessiot to bigger classes, a differential equation. So if one can think a Kolchin variety is internal to the constant. If there is a finite set of solutions that together with constants generates all the solutions. So the thing that, okay, so in particular, Picard-Vessiot extensions are internal to the constants, because if you have the fundamental system and constants, you can generate all the solutions. And then this turns out to be enough to do differential Galois theory. However, here, some groups that are like algebraic but not subgroups of GLN can appear. Like abelian varieties can, in this world, for some equation, appear as differential Galois groups of some differential equations. So in fact, for example, if one looks at Weierstrass P function equation, then this equation, if G2 and G3 are constants, will be internal to the constants. And we'll have absolute Galois group, the abelian variety of this equation. So, so this is, so there is a generalization of the Picard-Vessiot theory. And actually, this is enough to prove this fundamental theorem of Galois theory. And yeah, I wanted to say something about that, but today I won't have time. So maybe let me say during the last 2 minutes about this program of classification of minimal sets. So what is known about this classification? So there is a very crude classification up to a relation called non-orthogonality. So non-orthogonality, if I have two Kolchin closed varieties, they are non-orthogonal if there is a correspondence between them that is finite to 1 on X and Y. Okay, so in algebraic geometry, for example, every curves would be non-orthogonal, every two curves.
X by a Kolchin variety.
Accent here will be, yeah, strongly minimal. Strongly minimal Kolchin varieties. I mean, okay, in general, they don't have to be strongly minimal for this definition, but then I want to state this theorem at the end, which is Hrushovski-Sokolovic. That up to non-orthogonality, strongly minimal sets are the following. We either have constants. So for example, if we have strongly minimal set that is internal to the constants, this is where it will run. Either we have a Manin kernel, of an abelian variety, not over constants, where this Manin kernel by definition is the Kolchin closure of torsion points. You take an abelian variety not defined over constants, you take torsion points and the smallest differential equation that it contains. Either it has disintegrated geometry. So this means that if you take two different solutions, there cannot be any relations between them, roughly. Okay, so maybe I'll finish here. But
Great, any questions?
So when you said enough to do differential Galois theory here, would that connect up to the earlier discussion if you were doing Galois theory over the field of constants?
So here, so in differentially closed field, constants are algebraically closed. So this is like this part. But yeah, if you assume that constants are not algebraically closed, you mean can you do like Picard-Vessiot with?
I just meant like in the earlier discussion of Galois theory, there was a K and there were extensions of K, and the K that would be relevant to this would be the constants in the differentially closed field, or the
No, so you can take, for example, this differential equation that Weierstrass P function satisfies, and it's not linear homogeneous, but still you can adjoin it to C of t, and you can study symmetries of this differential equation. So automorphism of this adjoint differential field, and then you will get a Galois correspondence there. Yeah. Yeah, maybe Spencer, your first.
Oh, sorry. Does every algebraic group show up as a Galois group?
So yeah, I think over some differential field, I think it is known, yes. But okay, I guess it depends because maybe if you it depends what do you mean every, because I guess you don't want to look at finite groups. But even finite groups, if you look at any field, yeah, okay. So yeah, I guess let's say the field of constants is algebraically closed, and you look at connected components, then I think.
Is it false that differential Galois theory works with this internal to the constant assumption?
Is it false that what? That it doesn't work?
Yeah.
So okay, so some things do work. So for example, because from this point of view, constants are just some curve, and you can do it over other curves. But then you don't look at you don't necessarily look at symmetries of field extensions, but you look at like here the point is you look at symmetries of some differential equation that fix this. So sort of you can think about this Picard-Vessiot theory where constants are always fixed. But if you replace constants by some different differential equation, which is strongly minimal, then you still can get some Galois theory, but it's not maybe exactly automorphism groups of differential field extensions, but you get some different algebraic groups.
But for most,
No, okay, not necessarily algebraic, sorry. Yeah.
They're not algebraic, sorry.
Like if you're internal to the constants, you will be algebraic over constants. But if you're internal to some other curve, then then you will get some definable group, so some like Kolchin constructible group. But it may not descend. It may not come from a group scheme over constant.
I see.
you're saying if you write, just so I understand, if I write like an arbitrary differential equation, with, also just polynomial derivatives in there, then there's with no conditions, I should expect no Galois theoretic sort of theory around that equation. Like for then if you have this kind of condition, then you expect some symmetry stuff. So is there any kind of, you say anything about practically where these kind of things arise, where you're internal to the kind of Kolchin equations?
Okay, yeah. So yeah, to check this internality.
Or not even to check, just is there a source of them that's ubiquitous?
Yeah, like I guess if there are some examples studied in nature where it happens.
Sure.
But yeah, for random equations, there are some results of the like general type results, where if you look at general type variety, it should be here in this sense. So like most of the things are very difficult and somehow, we don't have many are like higher genus.
Other questions?
We find theorem here, theorem and the notion that is the differential closure of CT Noetherian? I don't know.
Oh no, so the topology is Noetherian,
Uh-huh.
but yeah, if you take the differential, so the point is, maybe this is related to the other things, but like somehow if you have the field, for example, you have this chain. You have this chain of subvarieties. And here you have constants. So this is one-dimensional, this is n-dimensional, and this will be like omega-dimensional. And Noetherianity tells you that, like, okay, if you go down, you will be able to only go down finitely many steps. But yeah, I don't know if that helps. So I wouldn't consider this as like this may be a matter of terminology. It's like Noetherian, but of rank omega. Like we need more steps.
And you know the dimension of C to the n?
So it would be omega to n.
To the n.
Wait a minute. Yeah, because I guess every dimension right. So I guess so okay, but there are various ranks here coming from model theory. So there is Morley rank, there is U rank. There are various ranks that have different properties, and they do not necessarily always compare. So here it's not clear. Like for various situations, there may be better or worse notion of dimension. Yeah.
Any questions? Okay, if not, let's take Michal again.